Hi, my name is Tina Wu, and today I'll be presenting my presentation on IoT network traffic analysis, opportunities and challenges for forensic investigators. I'll be giving you a brief introduction on the topic, what motivated us to carry out this research, a detailed breakdown of the methodology we took, and a presentation of our results following the experiments, and finally we talk about the tool developed that will aid an investigator in carrying out the analysis. So with the increasing number of IoT devices and the potential evidence on them, it's become more and more important when working on criminal cases. When IoT devices are involved in investigation, it is important to make a decision on how to collect evidence, such as to be collected from the memory or the network layer, where this work focuses on the latter approach. Typically, this involves examining the network traffic between the devices and the system it communicates with. So this is looking at all the communication channels of an IoT device, such as the cloud and the mobile app, looking, for example, for unencrypted information. So what motivated us to carry out this research? So we wanted to understand what metadata in a network traffic can be used for forensic evidence. So there's been a significant amount of research on IoT devices on network traffic from various angles, such as the security perspective. However, most existing research does not focus on the forensic implications. This helped us formulate 4 research questions. First research question is we wanted to investigate was, does a IoT device expose ports that allow an investigator to connect or access the device? Well, previous research has shown that many IoT devices expose their remote ports, so such as using port 22, which is SSH. This would allow an investigator to easily access and acquire the file system and obtain evidence for an investigation. So we set out to study if remote access was widely available or if this was limited to a subset of IoT devices. Our second research question was, do IoT devices use encryption when sending or receiving information from the cloud and their mobile app? It's often stated in previous research that the majority of IoT devices encrypt their communication channels. This makes it very difficult to obtain any useful forensic traces. So we set out to investigate whether this assertion is correct, and if not, whether certain devices were more prone to sending clear text data. Our third research question was, do IoT devices' mobile apps use encryption when sending or receiving information? So being able to observe the content between a mobile app and the cloud can be of forensic interest. So even when encryption is used, we can use a proxy server to decrypt the HTTPS traffic. So we set out to investigate what content is sent between the IoT device mobile app and the cloud. Our last research question was, to which countries do IoT device and mobile apps communicate or establish connections with? This would help provide an indicator of where data resides. So it's often highlighted in previous research that data is spread across many different countries. We also make the assumption that data from IoT devices are either stored locally or in the same country or within the EU at least. So we want to investigate whether this is true. So we now give a detailed breakdown of our methodology. So for experiments, we use network traffic obtained from 2 sources for our data sets. Dataset 1, this is network traffic collected from 17 IoT devices connected to our testbed. Dataset 2, this was an existing dataset created by previous research where the authors used their dataset to classify IoT devices traffic into various categories using machine learning, so whether this was a light bulb or a home assistant. They collected traffic from 28 IoT devices, such as cameras, switches, and hubs. Given the sheer amount of data they collected, we randomly selected only 7 days from the dataset and excluded any devices that overlapped with our experiments. This left us with 15 IoT devices. So once we merged the datasets together from dataset 1 to 2, this created 32 IoT devices we used for experiments. When selecting IoT devices, 17 IoT devices, we had selection criteria. That it was from a variety of families, so it included hubs, camera switches, and smart speakers. So this was to ensure that we had different manufacturers as well, so it represented a sample of devices available on the market. Popularity, we searched various popular outlets, Amazon, eBay, and we selected devices based on popularity, average customer rating, and reviews. This was to ensure that we selected devices that were more likely to be used by the consumers. Also, we selected whether a device, compatibility with virtual assistants. So when looking at popular devices, we found that users often favored devices compatible with Amazon Alexa or Google Home Mini. So if we had a choice between the 2 particular devices, we chose the one that was compatible. Network traffic was collected from various communication channels in our IoT environment. So we first carried out port scanning. We then collected network traffic from the 3 different communication channels of an IoT environment. We then used a proxy server to examine the network traffic between a mobile app and the cloud to intercept HTTPS traffic. Finally, we established the location of the data. So to answer research question 1, does an IoT device expose ports that allow an investigator to connect or access the data or access the device? So the aim of this was to carry out port scans to identify which open ports, which then can allow an investigator to connect to the device. We used Mmap to do a quick scan for open ports. We then used appropriate software such as the browser to open ports, to access ports 80 and 443. We then used PuTTY to access port 22. We found the results. We found that the majority of devices use well-known ports or proprietary ports. Only one device allowed remote access. This was the Vera hub, and this was port 22. The root path was also written on the hub, so this allowed us easily to gain remote access. We found the Victor Cam and the Wansfield Cam exposed a large number of TCP and UDP ports. This was in contrast to 2 other smart cameras, the Xiaomi and a Y-Cam, where all the ports were closed. Although it's beneficial to have all the ports closed from a security perspective, but obviously prevents an investigator gaining remote access to acquire the file system using traditional forensic tools. So the network traffic analysis was divided into 3 parts: whether the device used encryption, whether we could decrypt the network traffic using HTTP proxy, and location of the data. As an initial step, when we looked at whether the device used encryption, we manually analyzed all the network traffic in NetMiner and Wireshark. In NetworkMiner, we used the clear text dictionary to carry out a customized search, and in Wireshark, we carried out a string search on the network traffic of each device, searching for any device identifiers and personal information such as names, emails, and passwords. To find an easier method to identify if traffic was unencrypted, we used entropy tests, which is we use a tool called ENT, which analyzes the packet payload to look for unencrypted information. So the test values runs between 0 and 8. High entropy value indicates there's randomness in the payload, which is most likely encrypted. Anything closer to 0, which is low entropy, there's more likely to be clear text. Although there's no definite threshold, we set our threshold level to 7 to avoid missing any encrypted traffic. We then set up the proxy server to intercept any traffic between a mobile and a cloud. We used the proxy server Fiddler, and then mobile device, Android mobile device, and ran intensive various interactions between device login and log off. In total, we examined 13 mobile apps. We then manually analyzed the data in Fiddler. In terms of location of the data, we used using the metadata, we primarily focused on location of the connected cloud services. So we developed a Python script to extract a destination IP address, host field, and number of bytes to that server from each device. We then used the destination IP address to identify the location using Geo IP database, and the host address using WHOIS data to identify the IoT cloud infrastructure. Research question 2: do IoT devices use encryption when sending and receiving information from the cloud and the mobile app? So we examined the unencrypted traffic for any evidence potentially useful for investigation. We found the majority of devices encrypted their network traffic. This was especially between the mobile app and the cloud. Overall, we found 9 devices use no encryption with the cloud or mobile app. 7 devices use no encryption between the device to cloud. 3 devices use no encryption between the mobile app to device. Specifically, the Xiaomi camera communicated to the cloud using no encryption, and the D-Link camera communicated to the mobile app in clear text. While both these devices showed high entropy scores, even though because they didn't use any encryption, we found that because the devices used video compression, it meant that the entropy test would fail on these devices, especially cameras. So we've also found that when a Xiaomi camera detected motion, it would send an unencrypted video, the MAC address and timestamp. This was also present in the mobile, in the D-Link camera when it was activated, when the mobile app was activated between the device and the mobile app during live streaming, where partial JPEG images were present in the HTTP header in clear text. The Samsung camera also sent unencrypted HTTP post requests to the cloud that exposed unique identifiers such as the MAC address, username, serial number, timestamp, and other user-specific device names. The 3 devices manufactured by Wivrings all sent clear text data through HTTP post requests. More specifically, the Wivrings smart scales displayed considerable amount of user information. Weight, height, mainly in HTTP post requests. So all this data is sensitive and helpful not just identifying the user, but also their physical characteristics. So research question 4, do IoT device applications use encryption when, mobile applications use encryption when sending and receiving information? So the mobile app to cloud, this was the communication between the mobile app cloud, and we found 7 to 13 apps allowed a proxy connection, where the rest used certificate pinning. So what we found was when we opened the Wide-Cam mobile app, it would send a list of URLs which contained the motion captured, the username, user ID, and API key. We've also found some more unusual activity from the TP-Link camera. We opened the app, it would take a snapshot, which included a timestamp and a URL link to the JPEG snapshots. Note, we weren't actually able to control or disable this functionality. So from the same mobile app, we also captured HTTP GET request, which exposed the basic authentication field that contained a username and password to log in for the device. This was only encoded in base 64, so this can be quite easily decoded. Research question 4, to which countries do the IoT devices and apps communicate established connections, which can then give an indication where the data resides? This was to identify the destination that the data traverses. We found that overall, 26 of the 32 devices terminated in the US, as shown in this table. This is unexpected, as the closest Amazon data center obtained data center to our testbed is in UK, is actually in Ireland. So this shows the flow of the traffic to the top 10 countries. The height of the bands correspond to the number of bytes set by each device. Overall, we found that 75% of these IoT devices sent data to multiple destinations. From an investigative point of view, this is interesting, as multiple destinations and jurisdictions can potentially cause delays in gaining access and security in the data. Next, we examined the devices that contacted the most destinations. We found that the light bulb, one of the light bulb actually contacted over 28 destinations. When compared to other devices such as smart cams and smart hubs, we found the light bulb had limited features, so it's surprising that it contacted that many destinations. So tool creation, although our results can be found using separate open source tools, it would require an investigator considerable time to actually manually extract the data. So consequently, we developed a tool called IoT Network Analyzer, which was developed in Python to automate the process. The tool has the following 4 main features. It has the entropy calculation, so it can identify all sessions that are in clear text using a Shannon entropy test. It can locate the data by extracting the source and destination IP address. It can make the assumption of the geolocation, the usage of the security ports. So first, a list of ports is created with a total number of occurrences for each port. This list is then checked against a predefined list of 22 secure ports. Finally, it can then extract, the tool extracts any clear text information it finds in network packets. So this is just a quick demo of the prototype tool developed called IoT Network Analyzer. We're using it to analyze a PCAP file captured from one of the IoT devices on our testbed. It has several capabilities. One of them is command line interface, so that is a very interactive tool. So first we have to load the PCAP file that you want to analyze. The user can then select various parameters. So for example, the user selects G, which lists all of the IP address and the geolocation data. If the user wants to select E, it displays a list of the calculated entropy values. And if the user selects CN, it lists all the connections between the source and destination. And if the command PO is used, it overviews of all the ports used and occurrences of that port. Finally, we carried an evaluation of the tool's 4 main features and the performance of the tool. We used 5 PCAP files that we knew had clear text data and 5 PCAP files with no clear text data. So testing entropy tests, the entropy feature, we compared our results to a similar tool called ENT, and they provided accurate, identical results. Location of data, we used an external IP stack service for detection called IP stack service for detecting location, and we compared it to 2 similar services, IP2 location light and geolocation 2, which showed very little difference between the databases, meaning any of these databases would be equally suitable. We tested the feature of the usage of secure ports. To test the accuracy of this feature, we compared the results to a similar tool called T-Shark, and both tools showed identical results. In terms of clear text extraction, we compared our tool to Network Miner, and with our tool identifying the same key PCAP files which contained the identical results, they both showed the same clear text information. Finally, we tested the performance of the tool with respect to processing speed, central processing unit, and memory usage. The results from processing a PCAP of sizes ranged from 500 to 75,000 kilobytes are shown, and the results show that takes around 1 second to 6 minutes. A CPU and memory evaluation shows that the tool is not resource intensive, as it consumes only 60% CPU and has a very small memory footprint. Finally, our conclusion. So out of the 70 devices, we found only 1 device with remote access, and 2 smart cameras had closed all their ports. We found the majority of devices encrypted the network traffic. Devices that sent data in clear text were mainly smart cameras and smart healthcare devices, with smart healthcare devices exposing the most personal information useful for investigator to identify features of a person of interest. We found 7 of the 13 mobile apps allowed a proxy connections. Unexpectedly, some of these apps, when opened, would take snapshots, which included timestamp and URL link to the JPEG snapshot. While the majority of data we found was sent to the US, despite our testbed being based in the UK and a second data set collected in Australia. Thank you for listening to my presentation.